Scientists think it is very likely that an asteroid capable of destroying a city will strike the Earth every few hundred years. The result could be unimaginably catastrophic. That's why teams of scientists are developing ideas to help prevent such disasters and are working out ways to alter the orbits of asteroids.
Imagine a point in space where an asteroid and the Earth would cross paths at the same time and collide with one another. If you speed the asteroid up slightly, it will reach this point before the Earth does. The asteroid then passes harmlessly in front of the Earth, so to speak. Alternatively, if we slow the asteroid down, then the Earth passes the collision point first and the asteroid passes harmlessly behind the Earth. One solution would be to launch a relatively massive spacecraft designed to hit the asteroid at high speed.
The Fraunhofer Institute for High-Speed Dynamics in Freiburg is carrying out basic research into this method as part of the NEOShield European research project.
Asteroids typically consist of porous materials. Our first step is to gain a basic understanding of what happens when such materials are impacted by a projectile.
This light gas gun is one of the fastest accelerator facilities in the world.
The acceleration takes place over these 1.5 meters. The projectile sits here at the front. It's embedded in a plastic cylinder, a so-called sabot.
It can accelerate millimeter-sized projectiles to speeds of almost 10 kilometers per second. 10 kilometers per second is equivalent to 36,000 kilometers per hour. The NEOShield project team uses this facility to carry out laboratory-scale impact tests on materials similar to those found in asteroids. Instead of asteroid material, scientists have placed this stone block in the target chamber. They want to analyze with as much precision as possible how the material reacts to the impact of a projectile. These high-speed cameras document the experiment by taking up to 30,000 pictures per second.
Good. Lots of splinters, as we can see here. A lot of material has been ejected. Here's the transient crater, which is the crater that is formed during the initial phase of projectile penetration. The material here is very finely fragmented, as we can see. In this case, we can clearly see the transfer of momentum caused by the impact of the spacecraft or projectile. An additional transfer of momentum is caused by material being ejected backwards against the direction of the projectile. This has a forward propulsion effect similar to the way thrust is generated in jet engines by discharging mass backwards, which creates forward acceleration. The next step is to find out how we can increase this momentum transfer as much as possible by varying the projectile's speed of impact, its shape, and the type of material it's made of. But we also want to understand how the material composition of the asteroid affects the transfer of momentum. Relatively few large chunks. That's how it is with real asteroids too. We hope our research and technical investigations will continue on into a second phase. Ideally, we would like to be able to launch a space mission to test 1 or 2 deflection methods on a real asteroid. A real test mission is bound to give us a few surprises and will teach us a great deal.
And the experience gained will be very useful when it comes to saving our planet from an impending catastrophe.